Hi everybody, this video is going to be about vector-valued functions. So a vector-valued function is a function which has vectors as outputs. And the type of vector-valued functions we'd like to start with today, we can look at functions that spit out two-dimensional vectors as outputs. And one way to do that is to have those functions take in a single number or parameter and using one separate function of a single variable for each of the two components, say x and y components, we can then construct a vector output for that function. And these are called plane curves. We can also look in 3 dimensions. So I have some vector r that takes in a parameter t, and for each of the 3 components for x, y, and z, or for rho, theta, and phi, for instance, each could be a function of t in some way, and that would then return a vector for any given t input and get a vector out. And so in 3 dimensions, excuse me, we call those space curves. And we've actually already seen this before. So when we had parametric equations for a line in 2 or in 3 dimensions, we actually got there by thinking about vectors. And so if we've got that parameterization, we've actually got a vector-valued function for that parameter t that returns some vector. And so again, if we base those vectors at the origin, then for any given value of t, for a vector based at the origin, the vector points to some point on the plane. And when we had parametric equations for a line, different values of the parameter point to different places in the plane, but those all fell on a line. So we've already seen a vector-valued function before. We can do others, though, that aren't linear. So here's an example of a plane curve that's not linear in rectangular coordinates with the x-coordinate given by our parameter t cubed plus 1 and the y-coordinate given by sine of the opposite of negative t and then plus 1/2. We see this curve. And if we look at some different values of t, we show that those are identified with specific points on this curve. And just like we saw with parametric equations for a line, and then with these other examples, they're not unique. We saw that we could come up with different parametric equations for the same line. So they might identify the same line in space or on the plane, but the equations might look a little bit different. They might be using a different vector. They might be going backwards. They might be moving along the line faster at different speeds given different values for t. So just because we've identified some specific curve doesn't mean there's only one specific vector-valued function whose vectors point to lead to all the different points on it. There may be others, but we can certainly find vector-valued functions for some curves. And then if we want to look in 3 dimensions, here's an example of a vector-valued function that takes in some parameter and returns vectors that point to different locations along this curve. And so if you sort of take that vector r, and you can imagine as you change the value of t that vector r sort of spirals around and traces out this curve. And vector-valued functions we can finally break into talking about a little bit of calculus. This is true for vector-valued functions of any dimension, but with 3 dimensions, for instance, if I've got some vector-valued function and say the x component's given by some function f, and the y component's given by some function g, and the z component's given by some function h, what would it mean to take the limit as that parameter t approaches some specific value of r? Well, it means just what we'd like, that we can imagine what's happening as t approaches a within each of those component pieces. And so we can take limits of vector valued functions. And if we can take limits of vector valued functions like this, then we can also take derivatives. And so if I've got this vector valued function r, what do we mean, what do we think is going to happen if I try to take the derivative of r with respect to t? If I try to find r prime of t. Again, just like we'd like, and you can show by the limit definition of the derivative and what we just talked about with limits, that it's the same as taking the derivative with respect to t of each of the different component functions for r. What I'd like to leave you with then is thinking about what does the derivative mean geometrically. So if I can find the derivative of some vector valued function, what does that derivative mean? What does it have to do with the picture? So think about that, and we'll talk about it in class next time.